meet my bride. Let's go for a ride in my newfangled automobile. Just where we will go, nobody knows, but it's sure a great way to feel. Behind the wheel of the speed meter steel, it's my newfangled automobile. Hello and welcome to Vintage Car History. I'm Wild Bill. An engine is a machine that converts some sort of fuel or energy source into heat, which in turn is converted into mechanical energy that can be used for other things. For example, to power a car. Though the first engines were not necessarily used to make self-propelled vehicles, the principles learned over thousands of years of machine development eventually led to the modern engines that we enjoy today. So let's take a drive through history along the road that brought us engines. We'll start with a machine. In simple terms, a machine is an energy converter. It takes whatever force is applied to it and does something with it that the aforementioned force could not otherwise do. Machines have been around for thousands of years. Levers, pulleys, screws, wheel and axles, wedges, and inclined planes. These 6 basic machines are the basis of pretty much anything that can be called an engine. Evidence of basic machines goes back to the Stone Age. Wedges have been used for splitting timbers and stones far before recorded history, and the inclined plane, along with levers, were most likely used in the construction of such ancient projects like Stonehenge and the pyramids of both Egypt and the Americas. And the wheel and axle is known to be in use by many civilizations worldwide by 3000 BC. Yet, machines weren't written about very much until the first millennium BC. Archimedes was amongst the folks of antiquity that first began to describe basic machines, as well as some unknown Chinese scholars of the same period. The machines they wrote about were quite varied. Water wheels that powered mills and other industrial functions, pumping machines, geared astrolabes, and even odometers. In the European and Chinese classical era, machines, both large and small, became part of daily life. Yet these early machines were not engines per se. An engine will use heat for its power. And the first man to document the workings of an actual engine did so in the 1st century, at around the actual lifetime of Jesus Christ and his apostles, Heron of Alexandria. As far as we know, Heron was born somewhere around 10 AD and was one of the scholars at the Great Library of Alexandria. Some of his writings survive, which include quite a number of inventions: coin-operated vending machines, the first use of a wind-powered machine, in his case it powered a pipe organ of sorts, the syringe, and a machine that could move water with a piston, the force pump. And amongst his writings is a crude diagram of the first true engine. This engine is called an heliopile. The way it works is very simple. A large covered bowl is filled with water and a fire is lit underneath it. From the lid of the bowl, 2 pipes are attached and bent towards each other at the top ends. Between the pipe ends, a metal ball is attached in a manner that it has bearings where it connects to the pipes, allowing it to spin, and that the pipes can in turn supply steam to the ball as it's produced in the crude boiler bowl beneath. This sphere has 2 small pipes attached to its equator, these being like rocket nozzles facing an opposite direction. When steam enters the bowl through the 2 large pipes that it's mounted to, the much smaller directed nozzles exhaust the steam with more pressure behind them, causing the ball to spin. Heat was used to make steam, which in turn was converted into mechanical motion. Though there is no record of this engine being used for any specific purpose, it was, nonetheless, the mitochondrial eve of all engines. For the next 1500 years or so, more writings about machines and their applications were penned around the world. It's fair to say that Leonardo da Vinci was particularly prolific in that regard. Yet these were about machines, not engines. So for the next significant engine design, we must go to China in the mid-17th century to see the drawings of a true engine, and in this case, it powered a vehicle. And the man that designed and built the thing also had to go to China to do it, Ferdinand Verbiest. Verbiest was a Flemish polymath, theologian, mathematician, linguist, musician, engineer, astronomer, yeah, he did it all. Born in Pittem in what is now modern Belgium in 1623, he was both a genius and well-schooled, eventually becoming a Jesuit priest in the Roman Catholic Church. Trained by said church to be a missionary, he was sent to China to the court of the Kangxi Emperor, the third and longest reigning of the Qing dynasty. There he would teach Catholic theology, philosophy, music, and whatever the emperor fancied. And one of the emperor's fancies was new technologies. Verbiest came up with a new technology, which was described as an automobile. Completed in 1681, it was a four-wheeled cart of iron construction with a fifth wheel at the front for steering. A boiler was in the center of the cart with a nozzle on it, much like an alembic used in distilling. This nozzle pointed into what was a very basic steam turbine. The turbine then powered the rear wheels through a crude but functional differential. Verbiest made a model of this for the emperor, a little over 2 feet long, and could move about on its own for about an hour before running out of fuel and steam. It's a huge stretch to call this a car, as it was never built large enough to carry passengers, but it was, as far as we know, the first vehicle to be powered by an engine ever built. The next step would be engines with pistons. It's true that many of the inventions by Heron of Alexandria had pistons, his syringe and force pump being two examples. But using heat to power a piston to make an actual engine came at the turn of the 18th century. Thomas Newcomen was responsible. Born in Dartmouth, England in 1664, he was himself an ironmonger as well as a Baptist preacher. His company made tools for the various mining industries in Britain at the time, and a common problem for miners is flooding. I mean, let's be honest, if you dig deep enough, you will find water. And a mine shaft filling with water when also filled with miners is considered a problem. And so, in 1712, Thomas came up with a solution. The Newcomen engine, also called the atmospheric engine, was the first engine that is known to be powerful enough to do meaningful work. Barely. Here's how it worked. A huge boiler made steam. This boiler released the steam from its top, controlled by a valve. Above the valve was a long cylinder which had a piston. The piston in turn was connected to a balance beam by rods and chains. The other end of the beam connected to a pump. Additionally, a tank filled with cool water was also connected to the cylinder through a pipe and valve. The boiler made lots of steam, but not at very much pressure, a couple of pounds per square inch at most. So when the piston slowly raised, it was not the power stroke. Raising the piston just let the pump lower to prepare to lift water. But once the piston was high enough in the cylinder, the steam valve would close and the valve controlling the cool water would briefly open. This would spray cool water into the cylinder and condense the steam, creating a vacuum against the normal air pressure we all feel. And it was this vacuum that was the engine's power stroke. The engine was slow in operation and very inefficient, but it worked. As long as you gave it a good supply of cool water and kept the fire going, it would work tirelessly. And the design remained pretty much unchanged for the next 50 years or so. It was a Scottish inventor, James Watt, who would improve the efficiency. In the mid-1700s, while working for the Glasgow University, he figured out a way to make it work better. Watt observed that the cylinder itself on a Newcomen engine had to heat up and completely cool down each time the piston went up and down. He correctly concluded that a huge amount of energy was being lost by this, and figured out a way to still keep the engine running without cooling the cylinder. His design included a new valve, an exhaust valve, where the steam could be routed to a separate condenser, that could simply be kept cool and make the process of creating the needed vacuum occur much faster. This made the atmospheric engine far more efficient and powerful. Watt studied just how much power the engine could produce and, through his experiments, came up with a way to measure the strength of an engine: horsepower. To do this, James had to first figure out how much power a horse produced, and then, based on that, come up with a formula that could be applied to any motive force. This is not as easy as it sounds, and it took several years and lots of experimentation and calculation to make it work. Now, he was a smart guy, and there's a lot of math involved, but here's the basic idea. Watt studied horses at work, turning millstones, plowing fields, and other things. Finally, he came up with a calculation of force. In his experiments, he observed that the average horse working a mill wheel could pull a load of 180 pounds of force, and over time, this could measure the foot-pounds of force that a typical horse could produce in 1 minute. His answer? 33,000. So, if an engine could produce that much force in 1 minute, it was doing the job of 1 horse, or 1 horsepower. Meanwhile, in France, Nicolas Cugnot would build a new kind of steam engine, one that would power the first road-going vehicle capable of pulling not only itself, but driver, passengers, and cargo. Indeed, the very first episode of Vintage Car History was about this man, so more info about him is just a click away, but here's a brief overview. Born in France in 1725, he was an engineer and a military officer, a captain in the French artillery. He had the idea to make a mechanical gun tractor, a steam-powered vehicle that could haul heavy artillery on and off the battlefield. But the atmospheric engines of the day were both too big, too slow, and not powerful enough to do so. So, he came up with a new engine design. Rather than use the vacuum of condensing steam, he chose to use the pressure of steam entering the cylinder to push the piston with force, making that the power stroke instead of the vacuum. This was no easy thing, as neither the metallurgy nor machining technology of the time were particularly up to the task. His design was to have a boiler producing up to 40 pounds of pressure, send the steam via a valve to 2 pistons in an alternating fashion. The pistons were connected together through levers and cams, as well as to the valve, so that when one was being pushed down by the steam, the other would be lifted and allowed to exhaust the steam. Uncle Nick's problem was that although the design itself would work on paper, to make a boiler that could handle that pressure safely, as well as the cylinders, seals, and a control valve, would be absurdly expensive using the technology of the time. Thankfully for him, King Louis XV took an interest in his work, and thus with government funding through the French army, his vehicle was in fact built and took to the roads of Paris in 1769. However, it took some 40 more years for the Industrial Revolution to catch up with the idea of a high-pressure steam engine, and it was Richard Trevithick that would invent the basic high-pressure design that would be the steam engine of choice for over a century. And again, episode number 2 of Vintage Car History is all about him in a click away. So again, here's a brief overview. Born in Cornwall, England in 1771, Trevithick was a mining engineer in the local tin and copper mines. Boiler technology and metallurgy had progressed quite a bit since Cugnot's time, and Richard believed that the time had come to design a new high-pressure steam engine with these advances in mind. Engines prior to his had what are called single-acting cylinders. The steam, or vacuum, would push the piston one way, and then the momentum of a flywheel or cam systems would push the cylinder back to the beginning of its power stroke. What Trevithick did was invent the double-acting cylinder. In his engine, high-pressure steam was introduced on one end of the cylinder, pushing the piston. Then, through a series of valves, high-pressure steam was brought into the other side, pushing the piston back. This made each time the piston changed position, or stroked, to provide power. This doubled the work the engine could do, and engines based on this design powered much of the industrial world. However, internal combustion engines were just around the corner. Keep in mind that all engines get their energy from heat. In an external combustion engine, the fuel producing the heat is not burned within the cylinders of the engine. This fuel can be anything from wood, coal, straw, lamp oil, or even the sun. But the heat that creates the energy is not generated in the engine itself. Not so with an internal combustion engine. A fuel is mixed with air or oxygen and ignites within the cylinder, creating the heat and energy that pushes the piston. And in the early 19th century, quite a few engineers and tinkerers across Europe tried to make such an engine, until in 1859, Etienne Lenoir made one that actually worked. Lenoir was born in 1822 in Belgium. He moved to Paris, France when he was 16 and was nothing less than a genius on the loose. He got into just about any techie stuff he could get his hands on, and one of those techs was engines. What he did was to take a standard steam engine of the time and convert it to being a gas-powered engine, or, to put it another way, turn an external combustion engine into an internal one. His engine had a single cylinder that was powered on both ends. Mixing the fuel, igniting it, and then exhausting the leftovers all happened with each stroke of the piston. It was not particularly efficient, but worked well enough for Lenoir to use his engine to power a wagon, making his creation, what he called the Hippomobile, the first vehicle with a gas engine. Now let's take a moment to clear up a couple of terms that are commonly used with piston engines: bore and stroke. Bore refers to how big the hole is in the middle of the cylinder where the piston goes up and down. It's an old math formula. Area equals pi times the square of the radius of the circle that makes up the hole. This can be measured in inches, centimeters, or whatnot. The stroke is the distance that the piston travels within the cylinder in either direction. The two combined is what gives us the displacement of an engine. For example, if a cylinder has 4 inches of area and the piston travels 5 inches within it, when you multiply them together, you get 20 inches. That's the engine's displacement. Now the term stroke is also used to denote how an engine works. When the piston completes its movement in one direction, that is a stroke. When it completes its motion in the opposite direction, that is also a stroke. But not all of the strokes are going to produce power, at least in modern engines. We commonly hear the terms 2-stroke and 4-stroke engines today, yet we just did hear the term 1-stroke engine regarding Lenoir's design. This is because his engine did not compress the fuel, but rather added fuel and air on each side of the piston. So power was applied to the piston on every stroke. So in regards to engine type, stroke can also mean how many times the piston has to go up or down before it produces power. A 2-stroke engine does so after 2 strokes, going up and down once. A 4-stroke engine produces power after 4 strokes, going up and down twice. Both engines are more complex than Lenoir's 1-stroke engine, but are also far more powerful. And the first of these to be invented was the 4-stroke engine devised by Nicholas Otto. Otto was born in Germany in 1832 and was a natural mechanical engineer from birth. Oddly enough, his degree was in business management and his first jobs were as a salesman, but he did his own tinkering in his own garage and by 1861 had designed and built the world's first 4-stroke gas engine. In Otto's engine, each stroke of the piston was given a separate task through valves at the top of the cylinder, which he referred to as the cylinder head. When the piston went down, a valve would open and both air and fuel would be allowed in. This is the intake stage. When the next stroke started and the piston went up, the intake valve would close so the piston would compress this mixture. Once at the end of that stroke and at the top of the cylinder, a timed spark would ignite and force the piston back down, the power stroke. Once the power had been made and the piston was ready to go back up again, another valve would open, the exhaust valve, to allow the spent fuel to be expelled from the cylinder. Intake, compression, power, exhaust. 4 strokes of the piston with one producing power, hence a 4-stroke engine. It was Carl Benz that came up with the two-stroke engine. This German engineer was born in 1844 and, being yet another mechanical genius, got his engineering degree by age 19. He started inventing all kinds of stuff, and among these was the two-stroke engine. In his engine, which first ran in 1879, the valves to allow intake and exhaust were not in the cylinder head, but rather strategically placed in the cylinder walls. This way, the ignition of the fuel and air mixture would happen when the piston was at the top of the cylinder, and in the process of going down from the power stroke would exhaust and bring in more air and fuel. On the next stroke, it would compress the gas-fuel mixture, and when finished, would start the process again. 2 strokes with 1 for power. To be fair, the two-stroke engine took a bit longer to be used in motor vehicles. It is simpler and can be made much smaller than a 4-stroke engine, but is also more difficult to balance and harder to lubricate. Thus, most two-stroke engines require the adding of oil to the fuel and as a result create more smoke and bad smells. But being simple, it could be made very small, and is, to this day, the engine of choice for small motorcycles and gas-powered hand tools such as lawnmowers, chainsaws, portable generators, and the like. And both types of engines work well when using the engine configuration invented by Rudolf Diesel. Though born in Paris, France in 1858, this German engineer came up with a modification to the compression stroke of an engine back in 1893. In Diesel's engine, the compression stroke only squished the air. Not until the air was fully compressed was a dollop of fuel added to the cylinder, which, if a low-octane fuel, will immediately ignite due to being suddenly exposed to oxygen while being compressed. Diesel's idea works well in both 2- and 4-stroke engines, though the engine itself must be made stronger and thicker to handle the much higher pressures involved. Oh, I mentioned motor vehicles a bit ago. So why are engines not motors, or motors engines, or are they the same? How could something with an engine be called a motor vehicle? To be technically correct, which I've heard is the best kind of correct, the reason an electric motor is not an engine is because it does not use heat to provide its motive energy, though heat is produced in the process of it working. Conversely, engines are not motors for the opposite reason. They require heat to operate. However, the two terms, engine and motor, are often mixed together in common vernacular outside of the circle of engineers and mechanics that actually care about the difference. So it's quite common to hear the two terms used interchangeably by non-gearheads. There are other engines that were developed. The radial engine, the rotary or Wankel engine, steam turbine engines, jet engines, rocket engines, but those are beyond the scope of this channel. Yet even these engines all began with the 6 basic machines of antiquity. Machines that, when heat was applied, would get to work and become engines. And it is because of the inventors of these machines and early engines that mankind learned how to turn up the heat and get down the road. Thanks for watching Vintage Car History, and we'll see you next week. Peace.